For most steam power plants, the source of energy is provided by the combustion of fuels such as coal, oil, gas, wood, and even waste products. In this video, we're going to see what it takes to burn and control the combustion of these fuels. We'll also look at the types of burner equipment that are installed to perform this task. The term fossil fuel is applied to fuels such as coal, oil, and gas, which have been formed over millions of years by fossilized plant life in the earth. On the other hand, wood is derived from recently cut living trees. However, all of these materials are combustible and burn in a similar manner. What is in these fuels which causes them to burn? Well, the most important combustible elements are carbon and hydrogen. Sulfur also burns but releases only a small quantity of heat. Other ingredients in the fuel, such as moisture, water, nitrogen, or oxygen, are vaporized. Other constituents of the fuel, notably metallic elements, are non-combustible and remain as ash after combustion has taken place. A typical analysis of coal may indicate the following makeup: carbon 70%, hydrogen 5%, sulfur 1%, nitrogen 1%, oxygen 2%, ash 12%, and moisture 9%. Actually, the moisture content consists of two components, that is, the inherent moisture in the mined coal, plus the surface moisture, which is picked up in transport and in storage in the coal piles. The moisture is not combustible, and neither is the ash. So in this particular coal, we have 21% of the total which does not enter into combustion at all. Moreover, this non-combustible material actually absorbs heat and so reduces the energy available for steam production. In a moment, we'll see how to calculate the heat content of fuels. Let's now compare this coal analysis with that for a typical heavy fuel oil. It is very apparent that this fuel will contain more heat than the coal, because look, it contains much more carbon and hydrogen. Also more sulfur, which provides some heat, but also causes more problems, as we'll see. The actual total of non-combustible elements, that is, the ash, is quite small. Nevertheless, this ash can still cause problems in operation, depending upon the actual ingredients. Now, as another comparison, let's look at the typical analysis of natural gas. Here again, the amount of carbon, and particularly the hydrogen contained in the fuel, is very high. Moreover, there is no ash or moisture or sulfur to contend with. These unwanted elements are removed, or at least significantly reduced by processing at the source. It is no wonder that natural gas is a preferred fuel when available. In comparison, we can see that wood as a fuel will not produce much heat because the amount of carbon and hydrogen is relatively small. The ash content is also small, but a large percentage of the wood makeup is in the form of moisture and oxygen. This has a lot to do with the method of storing wood, which is usually in the open air. The wood has a propensity for absorbing moisture from the atmosphere much more than other fuels. For this reason, wood is often dried as part of the preparatory process before it's fed into the boiler for combustion. But hang on here. We're getting ahead of ourselves. Let's back up and examine the chemical reactions which bring about combustion and release heat. The most vital factor is that oxygen must be mixed with the combustible material in order for it to burn. There are other requirements too, as we shall see later, but without oxygen it is quite impossible for combustion to take place. And where do we get this oxygen? Well, a small amount may be contained in the fuel, but generally we derive the required oxygen from the air, which is all around us. Air is composed of oxygen and nitrogen in the approximate ratio by weight of oxygen 23% and nitrogen 77%. So in order to create the combustion reaction, all that is necessary then is to supply air to a combustible element, such as carbon, and ignite the mixture. Provided sufficient air is supplied and the carbon burns completely, it forms a gas, carbon dioxide, represented by the symbol CO2. That is, one atom of carbon and two of oxygen. Theoretically, to completely burn 1 pound of carbon, we need to mix it with 2.66 pounds of oxygen. The resultant combustion process produces 3.66 pounds of CO2 and at the same time releases a large quantity of heat, 14,600 BTU. If we're dealing with metric values, then for 1 kilogram of carbon, we need to add 2.66 kilograms of oxygen to produce 3.66 kilograms of carbon dioxide. This reaction releases 8,111 kilocalories, or 13,933 kilojoules. Now let's look at the combustion of hydrogen. In this case, for each 1 pound of hydrogen indicated by the symbol H2, we need to add 8 pounds of oxygen. And this combination produces 9 pounds of H2O, that is, water. Actually, this water will be in the form of vapor because the temperature inside the furnace and all the way through to the chimney is way above the boiling point of water, 212 degrees Fahrenheit. The combustion of hydrogen releases a large quantity of heat, that is 61,500 BTU per pound of hydrogen. Sulfur, on the other hand, contains far less heat, that is 4,000 BTU per pound, and requires 1 pound of oxygen to combust. This reaction produces 2 pounds of sulfur dioxide, SO2. So if we know the percentage of each ingredient in a particular fuel, we can easily calculate the heating value of that fuel. As an example, let's take our analysis of a typical fuel oil. If we consider 1 pound only of that fuel, then its carbon content, 86%, is 0.86 of a pound. Multiplying this by 14,600, that is the heating value for 1 pound of carbon, we find that the carbon content of this fuel will produce 12,556 BTU. The hydrogen content is 0.095 pounds, and we find that this releases 5,842 BTU when completely burned to H2O. The sulfur content in each pound of fuel is 0.035 pounds, and multiplying this by 4,000, we find that the heat content for sulfur is 140 BTU. Summing all of these quantities of heat for the different combustibles, we find that the total heat content of this particular fuel oil is equal to 18,538 BTU per pound. In your workbook, we have performed similar calculations in order to find the heat content for other fuels based on the typical analysis given. The results are as shown here. You can see that natural gas is by far the highest in heat content, while wood is quite low. This means that we would have to burn about 3 times as much wood as gas in order to produce the same amount of steam. Looking at the analysis, it is apparent that the fuels with the highest hydrogen content have the highest heating value. On the other hand, high ash and moisture content result in low heating value. Sulfur is a distinctly unpopular constituent in fuel for 2 reasons. It can cause corrosion in boiler equipment unless special operating precautions are taken. The gas from combustion of sulfur, SO2, and SO3 is environmentally unfriendly, resulting in expensive measures to meet regulatory requirements. Note that fuel oil usually contains more sulfur than coal, while processed natural gas contains none. Knowing the heat content or calorific value of a specific fuel, we can calculate the quantity of that fuel that must be burnt to produce a certain amount of steam in our boiler. For example, suppose we need to produce 200,000 pounds per hour of steam at a pressure and temperature of 1200 psia and 1000 degrees Fahrenheit. How much fuel oil would we have to supply to the boiler? Well, looking at the steam tables, we find that the enthalpy in the steam leaving the boiler is equal to 1499.4 BTU per pound. Let us assume that the water entering the boiler contains 399.4 BTU per pound. This means that we need to add 1100 BTU to each pound of water passing through the boiler. The total heat required is 200,000 pounds per hour times 1100 BTU per pound equals 220 million BTU per hour. All of this heat must come from the combustion of the particular fuel which is supplied to the boiler. In this case, its heat content is 18,538 BTU per pound. So dividing the heat required by the calorific value of the fuel, that is 220 million BTU per hour, divided by 18,538 BTU per pound, the quantity of fuel indicated is 11,867 pounds per hour, say 5.3 tons per hour. Is that correct? Well, actually, this is not correct because we have not allowed for any losses in the boiler. Common sense tells us that the conversion into steam energy of heat released by combustion cannot be performed at 100% efficiency. As we shall see later, there are a number of losses in the boiler, the greatest of which is the loss of heat exhausted up the chimney to atmosphere. Generally, the efficiency of most modern boilers is about 87%. So we need to adjust our calculated quantity of fuel required for this. To do this, we divide the 5.3 tons by efficiency 0.87, and the result is equal to 6.09 tons per hour. If this boiler were to be supplied with natural gas instead of fuel oil, we would need to supply less fuel because of the greater heat content of gas. On the other hand, if coal is the fuel, then we would need to provide more. Over and above that, if we are burning coal, we have to make provision for handling the moisture content and also all of the ash which is contained in the coal. We'll be talking about this important subject later. Summarizing then, so far we've looked at the main constituents of fuels and also studied the combustion reactions so that we can calculate the heat content of each fuel. Of course, the release of this quantity of heat is dependent upon complete combustion of all of the elements, and that means that we must provide sufficient oxygen, or rather air, which contains the oxygen. We'll be talking about this in the next segment, but for now, it's time for a break. Please switch off the video and review this material in your workbook. One of the most important factors in efficient operation of a boiler is supplying the correct quantity of air for combustion. The optimum amount of air depends entirely upon the constituents of the fuel. For example, if a fuel contains a large amount of hydrogen, it will need a larger quantity of air than a fuel with low hydrogen content. Remember from our last segment that for each pound of hydrogen, we must provide 8 pounds of oxygen, that is 35 pounds of air, to effect complete combustion. Once again, let's take our fuel oil analysis as typical, and from this calculate the theoretical amount of air which must be provided to completely burn the fuel. To do this, we have to look at each element separately, that is the carbon, hydrogen, and sulfur content. We pointed out before that for 1 pound of carbon, we need to provide 2.66 pounds of oxygen, and this produces 3.66 pounds of CO2. In our example, 1 pound of fuel oil contains 86% of carbon, that is 0.86 pounds. Therefore, the theoretical amount of oxygen required for complete combustion, is 0.86 times 2.66 equals 2.2876 pounds of oxygen. The quantity of CO2 produced is equal to this number plus the amount of carbon provided, 0.86, and this equals 3.1476 pounds of CO2. Remember, all of this is the result of burning just 1 pound of the particular fuel oil. Now let's look at the hydrogen content, that is 0.095 pounds. Multiplying this by 8, we find that 0.76 pounds of oxygen needs to be provided, with the resultant production of 0.855 pounds of H2O in the form of vapor. The sulfur content for each pound of fuel is 0.035 pounds. We need to provide the same quantity of oxygen, that is 0.035 pounds, and the resultant reaction forms 0.07 pounds of sulfur dioxide, SO2. So summing up the total oxygen requirement, we find this comes to 3.0826 pounds. But look, there is already a small quantity of oxygen contained in this fuel, that is 0.002 pounds. So we need to provide less, that is 3.0806 pounds. As we mentioned before, the oxygen is contained in atmospheric air. So the total theoretical quantity of combustion air that must be provided is equal to 3.0806 divided by 0.23. And this equals 13.39 pounds of air for each pound of fuel burned. Note that we refer to the theoretical amount of air required. And the reason for this is that experience shows that we actually need to provide more than the calculated quantity if we are to achieve complete combustion. This is because of the difficulty in achieving a thorough mix between the incoming air and the particles of fuel. Indeed, if we were to provide only the theoretical quantity of air as shown by calculation, we would probably end up with incomplete combustion in the form of some solid carbon particles, that is, unburned carbon, and some portion of carbon monoxide instead of carbon dioxide. Now, what is this about carbon monoxide? Well, another reaction calculation shows us that 1 pound of carbon plus 1.33 pounds of oxygen produces 2.33 pounds of carbon monoxide. In the process, it releases only 4,400 BTUs. This is less than 1/3 the amount of heat released by complete combustion of carbon to CO2. The implication of this is that where combustion is incomplete, we will have a certain amount of combustible gas, carbon monoxide, present in the flue gas. The consequence is a considerable heat loss up the chimney to waste. In order to ensure that combustion of the fuel is complete in practice, we need to provide excess air. The precise amount of excess air over the theoretical amount calculated really depends upon the type of firing equipment and the fuel itself. Speaking very generally, we may find that natural gas firing requires about 8 to 10% excess air. Fuel oil firing requires 10 to 15%. Pulverized coal will need about 20 to 25% excess air, while solid fuel on a grate may need as much as 50 to 100% excess air. We'll be looking at the different types of burner equipment later in this module. We've already mentioned that some heat loss is involved if we provide insufficient air for complete combustion. But we must also pay a penalty if we provide too much excess air. Now, why is this? Well, all of the combustion gas which leaves the chimney and exhausts to atmosphere carries with it a certain amount of heat. The temperature of this gas is usually about 300 degrees Fahrenheit. Consider then that if we increase the amount of theoretical combustion air by 100%, we would almost double the amount of gas leaving the chimney carrying heat to atmosphere. Clearly, this will result in increased heat loss and a decrease in boiler efficiency. So in order to obtain optimum efficiency, the operator has the difficult task of precisely controlling the amount of air supplied to the boiler. Too little and fuel will be wasted. Too much air and heat will be wasted. To assist the operator in this task, specific instrumentation and control devices are installed on the boiler, as we shall see in the next module in the series. The best way to monitor the effectiveness of combustion is to analyze the constituents of the flue gas as it leaves the boiler. Referring to our previous example with the combustion of fuel oil, we noted that for each pound of fuel burned, the flue gas contains 3.1476 pounds of CO2 from the combustion of carbon, 0.855 pounds of H2O vapor from the combustion of hydrogen, and 0.07 pounds of SO2, sulfur dioxide. But that is not all, is it? Remember that we supplied air, and 77% of this, by weight, consists of nitrogen. Multiplying our theoretical quantity of air required by 0.77, we find that the flue gas includes 10.315 pounds of nitrogen. Actually, this nitrogen does not enter into combustion and does not help at all in the combustion process. Rather, the inverse, in that it contains a lot of heat and carries this to atmosphere. However, there's nothing we can do about this, as we need oxygen, and the only practical way of acquiring large quantities of oxygen is from the air which surrounds us. Now remember, these values represent the weight of the different gases produced for each pound of fuel burned. Adding this together, we find the total comes to 14.382 pounds. And what did we put into the boiler? Well, first, for each pound of fuel, only 0.992 pounds entered into combustion. The remaining 0.8% consists of ash, which does not burn. Adding the combustible material to the quantity of air supplied, 13.39 pounds, the total comes to 14.382 pounds, the same value. Knowing the total quantity of gas, we can calculate the percentage for each of the constituent gases. In this particular case, CO2 makes up about 22% of the total, with nitrogen forming approximately 72%. So it is apparent that one way to monitor the effectiveness of combustion is to analyze the content of flue gas. However, in practice, it is difficult to accurately measure these proportions due to the fact that the water vapor may condense in the measuring instruments. The preferred method is to measure the proportion of excess oxygen which exists in the flue gas. Let's suppose in the case examined that we actually supplied 10% excess air. That is 13.39 times 0.1 equals 1.339 pounds more air than the theoretical calculation shows to be required for combustion. This excess air will contribute 0.308 pounds of oxygen and 1.031 pounds of nitrogen to the flue gas. So the total weight of flue gas for each pound of fuel burned is now 15.721 pounds, including 0.308 pounds of oxygen. The percentage of oxygen is therefore 1.96%. This is a typical target value for oxygen in flue gas, as indicated by monitoring instruments on the boiler when burning oil. In your workbook, we show the calculations for air requirements and flue gas analysis of our other selected fuels. But I'm sure you've all had enough of these calculations by now, and so have I. But really, this material is necessary in order for us to better understand the practicalities of operating different types of burner equipment. And we'll be looking at this in the next segment. Before getting into that, however, we must look at one more important item, and that is the effect of moisture in the flue gas. We have already seen that the combustion of hydrogen releases a lot of heat and also produces water vapor. In the example studied, this came to 0.855 pounds of water for each pound of fuel oil burned. As we pointed out, this water is in the form of vapor as it passes on through the boiler and out the chimney to atmosphere. This means that the latent heat which is contained in this vapor cannot be recovered. This adds up to a fairly significant amount of heat, 970 BTU per pound of water. In the boiler in question, this represents a heat loss of 0.855 pounds times 970 BTU equals 829.35 BTU for each pound of fuel burned. The real implication of this is that all of the heat in the hydrogen contained in the fuel is in fact not available. In other words, the recoverable heat content of the fuel oil is actually 18,538 minus 829.35, and this equals 17,708.65 BTU per pound. This value is actually known as the lower calorific value, indicated as LCV. The higher number that we quoted earlier is known as the HCV, higher calorific value. When comparing fuels and looking at the efficiency, it's essential that we make ourselves aware of exactly which value for heat content is being quoted. In the USA, it is usual to quote the higher calorific value. The logic of this is that we have to purchase all the fuel even if some of the heat cannot be recovered. In fact, as we know, other heat losses are far greater than this amount. However, beware, in many other situations, for example, in many European plants and European manufactured equipment, the quoted efficiency is based on the lower calorific value. This would, of course, provide an apparent higher number for efficiency. Clearly, if the heat input to the plant is indicated at a higher value, then the calculated efficiency would come to a lower number. Now, I'm sure you're pleased to know that it's time for a break. Please switch off the tape and thoroughly review this material in your workbook. In the last two segments, we have discussed at length the supply and control of air for combustion. But that's not the only factor which governs the burning of fuel. In addition to air, we need to provide other conditions in order for the fuel and air to burn properly. These conditions are commonly known as the 3 T's: temperature, turbulence, time. The first refers to ignition temperature. Combustion will not take place without the fuel and air being exposed to a high enough temperature, known as the ignition temperature. For example, a fuel oil storage tank is vented to atmosphere. Air and fuel are in contact over a wide area, but combustion does not take place, thankfully. Similarly, coal is transported and stored with exposure to atmosphere, but it is rare that self-ignition occurs. In order to provoke combustion, some form of ignition must be provided, usually in the form of a pilot flame or an electric arc. Once the fuel and air mixture start to combust, the ignition becomes self-sustaining and no further help is required. The second item, turbulence, is extremely important. It is vital that the air comes into intimate contact with each tiny element of the fuel. In order to ensure this thorough mixing, some form of turbulence is created as the fuel and air enter the boiler through the burner equipment. Even when the fuel and the air are ignited and thoroughly mixed, a certain amount of time is required before the combustion process is completed. Initially, only partial combustion takes place, often forming carbon monoxide. Later, as the gas passes higher into the furnace, further mixing with air provides complete combustion. In fact, in many boilers, a portion of the combustion air is injected at a point higher in the furnace in order to assist in completion of the combustion process. This air is generally known as overfire air, or OFA. Now, there are many different types of burner equipment installed, generally for different fuels, and perhaps for different grades of the same fuel. As we study these various types of burners, we should keep in mind that the objective in all cases is to provide the correct conditions for combustion, that is, temperature, turbulence, and time, and also to provide control over the supply and distribution of fuel and air. In this segment, we'll take a look at combustion equipment for burning liquid and gaseous fuels. Here we see a typical fuel oil burner arrangement. Several burners are provided so as to allow for changes in heat input to the boiler to meet changes in steam demand from the boiler. Individual burners can be taken out of service to reduce load. The quantity of fuel supplied to each burner can also be adjusted. Fuel oil is fed through the burner gun under pressure and forced into the boiler through the burner tip. Air is blown from the wind box and enters the furnace through a diffuser which surrounds the burner tip. The objective of the diffuser is to impart a swirling motion to the air so as to create turbulence and improve mixing with the oil. Although the total quantity of combustion air is controlled at the FD fan, distribution between the burners is affected by local dampers. This is necessary because certain burners, due to their location in the wind box, may receive more and others less than their correct share of air if the local dampers are all set to the same position. Adjustment may be made manually or by remote control on modern boilers. The burner tip is designed to break down the fuel into very tiny particles, a process known as atomizing the fuel. The objective is to increase the surface area of fuel available for contact with air and so promote intimate mixing. Atomization is achieved by forcing the oil through a series of very small holes in the burner tip. A swirl plate is also fitted at the tip just ahead of the nozzle so as to impart a twisting motion to the fuel spray as it enters the furnace. Two methods are used to provide the pressure necessary to force the oil through the burner tip. These are known as steam atomization and oil pressure atomization, known as mechanical atomization. In the steam atomizing burner, oil is supplied to the burner at a pressure of about 100 psi. Atomizing steam is fed into the burner barrel at a pressure of about 150 psi, and this serves to force the oil through the holes in the burner tip. The steam supplied for this purpose is usually saturated steam taken from the auxiliary steam system. By adjusting the fuel oil delivery pressure, we can control the amount of fuel injected into the furnace by the burner. The atomizing steam pressure will have to be adjusted accordingly, usually by automatic controls, in order to maintain the required pressure differential. In the so-called mechanical atomization system, the fuel itself is supplied to the burner at high pressure, say 750 psi, and this is sufficient to force the oil through the burner tip. Control of fuel input to the furnace is usually achieved by adjusting the supply pressure and leak-off return from the burner. More about this in a future module. In order to help achieve good atomization, heavy fuel oil is heated to a temperature of about 200 degrees Fahrenheit in order to reduce its viscosity. The pressure and temperature of fuel oil is raised in a pumping and heating unit. We shall be looking at this auxiliary equipment and features of fuel storage in other modules in this series. Light oil, such as diesel fuel, is normally used for boiler startup. The advantage of this is that no heating is required, as its viscosity is already low. Also, mechanical atomization can be achieved at quite moderate pressure. Startup burners are located in the throat of each heavy oil burner, with the flame directed so as to provide a source of ignition when heavy oil injection commences. But how do we light off the startup burner? Even though diesel fuel is relatively easy to ignite, we still must provide some source of flame for ignition. Well, in the old days, this was done by the operator inserting a rod with a flaming rag at the tip. Today, the prime ignition to the startup burner is provided by an electric arc. In starting up the boiler, specific operating procedures must be observed for safety reasons, and we'll be looking at this in the next module. As atomized fuel oil and air enter the furnace, they burn with a bright flame when conditions are correct. Close to the burner, the flame is intense, with a temperature of about 3,000 degrees Fahrenheit. As the flame moves further into the furnace, it turns upwards towards the superheater, where eventually flames no longer exist. The hot combustion gas continues on through the boiler convection pass. A physical observation of the flame can give some indication of the effectiveness of combustion. For example, a dull red flame with black streaks indicates that combustion is poor, perhaps due to insufficient combustion air, poor atomization due to a defective burner tip, low fuel supply pressure. On the other hand, a short white flame with sparks flying is a sign of too much excess air. With experience, the operator learns to make the fine adjustments necessary to obtain the best combustion. So far, we have considered the location of burners to be along the front wall of the boiler. In some instances, burners are also located along the back wall. A more common arrangement, however, is with burners located at each of the four corners of the boiler, like this. Typically, we may have, say, 3 burners in a vertical arrangement at each corner. That is a total of 12 burners. The orientation of the burners is arranged so that the fire forms a rotating ball like this. This arrangement, known as tangential firing, is claimed to create greater turbulence, resulting in cleaner combustion. There are several other so-called liquid fuels available on the market today, where an emulsion of water carries tiny particles of coal or pitch in suspension. This mixture is injected into the furnace through a burner similar to the fuel oil burner. This could perhaps be considered as a replacement for fuel oil if the source of supply dried up completely. However, there are several drawbacks. One is that the water carrier, on entering the furnace, absorbs a large amount of heat as it evaporates, so reducing the amount of heat available to produce steam. There are also a number of problems involved in handling this type of fuel. However, this subject is really beyond the scope of this present program, so let's move on to examine a very popular fuel, natural gas. Firing with natural gas has some similarities to oil firing, and it is certainly the simplest fuel of all to burn. In most installations, the gas requires no preparation at all, as it is delivered under pressure directly from the supplier. Therefore, no storage facilities are required. The supply is metered at the incoming station, where its pressure is reduced to that suitable for the boiler. The gas is then supplied through a control valve to all of the burners. Atomization is not required, as this fuel is already in gaseous form. Natural gas, and oil for that matter, is highly volatile because of the high hydrogen content. This means that it ignites readily and burns quickly. Control of heat input to the natural gas boiler is similar to oil firing. That is, the flow of fuel to the burners can be adjusted by control of the fuel supply valve, at least over a certain pressure range. However, if the fuel supply is allowed to fall too low, we may get unstable combustion. In this situation, it's necessary to shut down one or more burners completely, and so raise the supply pressure to the remaining in-service burners. Now, we do have more to say about controlling combustion, handling the ash, avoiding slag and corrosion, but these operational items will have to wait until later. At this point, let's take a break, and then we'll come back and look at firing arrangements for solid fuels. For now, please switch off the tape and review this material in your workbook. When we speak of solid fuel, we are referring generally to coal. But remember, there are other solid fuels such as wood and even municipal and industrial waste. Let us first take a look at firing equipment for burning coal. The most common system on large boilers is that of pulverized coal. In this arrangement, the coal is ground into very fine particles as it passes through a pulverizing mill. The grinding of the coal is achieved by crushing with rotating heavy steel balls or rollers. The finer the particles of coal, the better will be the resultant combustion. You can see that this is similar to the case of atomization of fuel oil. The fine particles of coal are carried along with the stream of primary air, which is supplied to the burners and then blown into the furnace. The primary air usually makes up about 30% of the total air requirement for combustion. The remaining air, known as secondary air, is fed into the furnace around the primary burner. The type of burner shown here is normally employed for wall-mounted burners. For corner-mounted burners, a vertical arrangement is used like this, with multiple ports for the admission of primary air, pulverized coal, auxiliary fuel, secondary air, and tertiary air. In some cases, the tertiary supply of air may be provided at a location higher in the furnace. This over-fire air is added to help burn the relatively slow-burning coal. The boiler is usually equipped with several pulverizing mills, each of which supply a number of burners. For a tangentially fired corner arrangement, each pulverizing mill would probably supply one burner on each corner. There are two basic systems for providing the primary air. In the pressurized system, the primary air fan draws air from atmosphere and blows this through the pulverizing mill to pick up the particles of coal and convey them from here into the burners. So in this system, the mill actually operates under pressure. This has a certain disadvantage because any slight leakage in the mill results in fine coal dust being distributed to the atmosphere. It is almost impossible to keep this type of plant clean. The alternative arrangement is to place the fan, now known as an exhauster fan, downstream of the pulverizing mill. This creates a negative pressure which sucks in hot forced draft air and tempering air from atmosphere to provide primary air. As the mill now operates under a slight negative pressure, any leakage will be of air into the mill. But as with all things, there is a downside. In this arrangement, the exhauster fan is conveying both primary air and fine coal dust on its way to supply the burners. The result is a great deal of erosion and wear on the fan internals, requiring regular downtime for maintenance. Now, how do we control the heat input, that is, the fuel input to the boiler, from the burners? Well, this is done by controlling the quantity of coal and primary air entering the pulverizing mill. Coal is fed into the mill from storage hoppers located above. Adjustable feeders control the quantity of coal which is fed into the mill. Primary air can be controlled by adjusting the speed of the fan or by regulating dampers. Of course, as primary air and fuel are adjusted, the quantity of secondary and tertiary air must also be controlled at the forced draft fan. Over and above this, the distribution of air between primary, secondary, and tertiary systems must also be adjusted to provide the optimum combustion conditions. There is a limit to how far we can reduce fuel flow to each burner. This is because the fuel particles can no longer be carried in the airstream and may instead deposit on the bottom of the conveying pipework. At low loads, therefore, a set of burners and the associated mill will need to be taken out of service. We noticed when studying the fuel analysis that coal contains considerably less hydrogen than oil or gas. This factor makes it more difficult to ignite, particularly if the flow of fuel and air is reduced to a very low level. That would be at low boiler output. In this situation, we run the risk of the fire self-extinguishing at certain burners and then probably reigniting again, so creating a minor explosion or puff, as it is known. In order to maintain stability of combustion at low loads, it is usual to light the startup oil guns. These may be designed to burn diesel oil or heavy fuel oil in some cases. The objective is to ensure that ignition is maintained. We also noticed in the fuel analysis that coal often contains a considerable quantity of moisture. If this is fed into the furnace along with the fuel and air, it will create two problems. The moisture will absorb heat as it evaporates into vapor, so increasing heat loss and reducing the heat available for work. The formation of vapor may delay ignition and so reduce the stability of combustion. In order to avoid this, some effort is made to dry or partially dry the fuel before it enters the furnace. One way of doing this is to heat the primary air so that evaporation of the moisture takes place before the mixture enters the furnace. Often, a dedicated hot section of the boiler air heater is applied specifically for this purpose. We know that coal contains a considerable amount of ash. What happens to this during combustion? Well, the heavy particles fall to the bottom of the furnace, where they are removed by the ash handling equipment. The lighter particles, known as fly ash, pass on through the boiler in the gas stream to be removed in the precipitator or other particulate removal equipment. We'll be looking more closely at this subject, particularly in regard to slagging problems, in the next module. Now remember, here we are only looking at the main features of combustion equipment and not the fine details. You'll need to thoroughly examine the schematics and equipment in your particular plant. Another common method of burning coal on smaller boilers is by use of a traveling grate. In this arrangement, coal is fed from the chute onto a grate, which then carries the coal bed into the furnace. The grate is really a continuous conveyor made of very rugged material to resist heat, erosion, and corrosion. Initially, the bed of coal does not ignite as its temperature is too low for ignition. However, after a few seconds, as the bed continuously moves forward, its temperature rises due to radiant heat transfer from the existing flame and refractory arch, and ignition takes place. Forced air for combustion is fed up through the grate. The wind box beneath the grate is compartmentalized with individual damper controls, so that the distribution of air may be biased towards the front or back end as required. Generally, secondary air or over-fire air is admitted into the furnace at a higher level to complete combustion. As the grate continuously moves forward, the coal on the bed burns, leaving ash to be discharged into the ash pit, as the grate follows its continuous path and returns again to the coal feed. Control over the heat input to the boiler and consequent steam output is affected by adjusting the thickness of the coal bed on the grate, the speed of travel of the grate. The correct distribution of air is vital if complete combustion is to be obtained. Several inherent problems exist with this type of burning equipment. One is the potential for combustion to be incomplete and consequent discharge of combustible material into the ash pit and then to waste. Another potential problem is the failure of the coal bed to ignite, so that the whole bed of green coal may be discharged into the ash pit, while the boiler rapidly loses pressure. Another serious problem is caused by slag forming on the grate. This is due to metallic elements in the ash becoming molten and sealing the grate so that combustion air cannot pass through. This means that the coal cannot receive air for combustion. More serious yet is the fact that the grate overheats and may well distort and become physically damaged. Like all boilers, the traveling grate requires careful control of operation. Another type of traveling grate, known as the spreader stoker, employs a grate which is traveling in the reverse direction, that is, towards the front of the boiler. In this arrangement, the coal is thrown into the furnace at a higher level, like this. This means that a certain amount of combustion takes place in suspension, similar to a pulverized coal furnace. The remaining coal eventually falls to the grate, where it continues to burn in the conventional traveling grate manner. Ash is finally dumped into the ash pit as the traveling belt turns. This type of spreader stoker arrangement is sometimes used for burning waste material. Now at this point, we'll take a break and then come back and look at combustion equipment for burning low-grade fuels, such as municipal waste. Please switch off the video and review this material in your workbook. In this segment, we'll take a look at combustion equipment used to burn low-grade fuels. A low-grade fuel usually contains one or more of the following undesirable characteristics. Highly variable content, municipal waste, for example. Low heat content, high ash content, low ash fusion temperature. The effect of low ash fusion temperature is particularly onerous. It results in heavy slag formation on boiler tubes, superheaters, and other areas. This often leads to blockage of gas flow through certain sections of the boiler, as well as loss of heat transfer and consequent reduction in boiler output. The term low-grade fuel is used to describe such items as municipal and industrial waste, agricultural waste known as biomass, coal with low ash fusion temperature, petroleum coke, wood waste, waste from coal treatment facilities, peat. Ideally, waste or refuse should be sorted before it is fed into the boiler for combustion. That is, the non-combustible materials, such as glass and metals, should be removed so that combustible material only, such as paper, wood, cloth, etc., is supplied to the boiler. Generally, waste material and wood are burned on a fixed grate, usually sloping like this. Combustion air is fed up through the grate and needs to be carefully controlled so as to complete combustion and not blow the material off the grate. The ash eventually falls to the bottom of the slope and enters the ash pit. In another common arrangement for burning refuse, the material is burned on a dump grate, which intermittently opens like this to dump ash. Spreader stokers, as shown in the last segment, are also employed to burn waste material. There are, of course, many variations of these schemes for burning solid waste. Indeed, this task appears to be as much an art as a science. Successful operation of these boilers depends very much upon the experience of the plant operators. Another type of boiler which is employed to burn waste and low-grade fuels uses fluidized bed combustion. There are several different configurations of this type of combustion, each known by a descriptive title, such as FBC, fluidized bed combustion, AFBC, atmospheric fluidized bed combustion, PFBC, pressurized fluid bed combustion, CFBC, circulating fluid bed combustion. These different categories actually represent different degrees of sophistication and efficiency of the unit. But they all rely upon the same principle. Combustion takes place in a bed, floating on the combustion air, which is fed up through the bottom of the furnace. This is often known as a bubbling bed. Particles of fuel and bed material, sand or fine gravel, are suspended in the air and gas stream, almost resembling a fluid, hence the name. Well, isn't this just like pulverized coal then? Well, no. The fluidized bed allows us to burn much larger particles than pulverized fuel. But what's the advantage of this type of combustion? Well, the fluidization creates excellent mixing conditions, and this allows heat to be spread evenly across the bed, with the result that good combustion takes place at a temperature of about 1600 degrees Fahrenheit. This is much lower than with other types of combustion. This lower combustion temperature has several advantages, especially when burning poor quality fuel. One is that the combustion temperature is well below the fusion temperature of most components of ash, so eliminating most of the slagging problems that are common with many low-grade fuels. This type of combustion is also more environmentally friendly, as we shall see in our discussion of this subject in the next module. Let's take a closer look at a typical design. In this arrangement, we see the main components, that is, the combustor surrounded by water wall tubes, the hot cyclone, the superheater zone, and the tubular air heater. Both fuel and limestone are fed into the bed at the bottom of the furnace. A screw-type feeder is used to control the rate of flow. Primary air is fed into the bottom of the furnace in order to keep the bed floating, that is, fluidized. The primary air is heated using outgoing flue gas as it passes through the tubular air heater. Over-fire air to the furnace is supplied above the main combustion zone. Auxiliary fuel burners are located in the lower combustion area for startup and occasionally to help maintain combustion stability. Ash is drawn off from the bottom of the bed below the grid through so-called bed ash drains. In many units, heat is recovered from the ash by fitting feedwater heat exchangers in this area. This also serves to cool the ash and make it easier to handle. The lower part of the combustion chamber may often be lined with refractory, but most of the furnace consists of bare water wall tubes. The cyclone is also lined with refractory, as the gas temperature here is in the region of about 1500 degrees Fahrenheit. We do not want to lose any heat in this area because the hot gases themselves go on to provide heat to the superheater. Solid materials are fed back into the furnace. At the bottom of the cyclone, the hot, solid particulate matter is collected and fed back into the combustion chamber. Some heavy ash particulates may fall out at this point and can be recovered from the hopper. Clean gas passes over the primary and secondary superheaters and on down through the air heater. From here, the gas passes on to the particulate removal devices such as a precipitator or fabric filter. Now, as this continues to be a rapidly developing field, there are many, many different arrangements of fluidized bed combustion in service today and currently being installed. Our objective here has been to just give you a brief look at the principles and major differences compared with other types of boilers. If you are actually working with this type of boiler, make sure that you study the details of your particular installation. You should be familiar with its operating features, its limitations, and the operating and safety procedures. In the next module in this series, we'll be discussing features of boiler operation in some detail, and we'll also look at environmental factors. Please switch off the tape now and review this material in your workbook.